Yes, good day, everyone. My name is Michel Oid, as said, I'm a professor in Leiden, Netherlands. It's a great pleasure for me to introduce Professor Hartland, Greg Hartland, from University of Notre Dame in Indiana, US. So Professor Hartland is very well known in the field of ultra-fast spectroscopy, ultra-fast chemistry. He has been working with molecules, aggregated molecules, semiconductors, metal nanoparticles, many different subjects. He has studied in Melbourne, University of Melbourne, Australia, and then he moved to UCLA for his PhD in 1991. He did his PhD at Penn, University of Pennsylvania, from 1991 to 1994. Where he worked on gas phase ultrafast chemistry. And since 1994, he's at University of Notre Dame. He has become a full professor in 2004. And he has received many awards, in particular, very recently, an ACS award for physical chemistry. And he's a fellow of many learned societies, AAAS in 2009, ACS in 2011, and Royal Society of Chemistry in the UK in 2014. So we are very excited to have him at our webinar, and we're looking forward to his talk. So Greg, the screen is yours.
Thank you very much, Michel. Start off. For us, it's the morning, so good morning, everybody. Hope it's a convenient time of the day for you. I'm going to talk about mainly infrared PHI measurements, and these are a collaboration with our friends at Notre Dame and the Kuno group. And the experiments I'll talk about have mainly been done by Jeremy Lee and Kyle Ashar, and also Brendan Brown and Ilya have contributed to these measurements. So just one slide on the different sort of things that we do. In my group, we have interests in looking at surface plasmons, as Michel said, ultrafast spectroscopy, mainly of metal nanostructures and metals coupled to semiconductors more recently. And we're also very interested in using transient absorption microscopy, which is a technique that was developed and invented by Michel. And we use that to look at different sorts of metal structures again, with a focus on looking at the vibrations of these structures. Understanding how they lose energy and how they interact with the environment, or how they change when you couple nanostructures together. The last part of our efforts are on developing methods to image nanomaterials, and this includes PHI as well as some other experimental techniques, and that's what we'll mainly be talking about today. So the emphasis is going to be on infrared measurements, and so I want to start by sort of showing what happens if you do a conventional infrared imaging experiment on a nanostructure. So this is an experiment where you simply have a objective for infrared light, which is going to be a reflective objective. The ones we use are Cassegrain objectives, and you take a mid-IR laser. I'll show you the details in the next slide. It's a OPO laser. And you focus it on a sample and scan around until you see a feature, which in this case was about 1 micron diameter polystyrene beads. Okay, so if you scan over that, if you move the sample through the focus, you'll see a absorption by the bead, so a decrease in the reflected light. This is actually a pretty big signal. It's about 25% of the light gets extinguished by the bead. And you're just detecting that with a regular IR detector. And so the spatial resolution here is determined by a couple of things, as has been discussed by Jixing Cheng a little bit earlier and Ilya. The main effect, right, is that you're using infrared light. So the diffraction limit is, the wavelength divided by 2 times the numerical aperture. So it's not all that great. In this experiment, our spatial resolution was about 8 microns, which is actually worse than what you would expect based on the diffraction limit. Pardon me. So this is about a 3 micron light experiment. So you'd expect to get maybe about a 2 micron spatial resolution. We're a lot worse. And this is another problem that you have in the IR, is that the objectives, Cassegrain objectives, are really pretty difficult to use. And in our hands, that's as good as we could do. So we really don't like Cassegrains. They're a bit of a mess, and they don't really give you great resolution, certainly not for us, not near what one might expect. So those are the problems with imaging, directly imaging in the IR, right? The wavelength problem, and also that the optics are kind of crappy, right? They're not as easy to use and not as well developed as what you have in the visible, where you have very high quality refractive objectives. So one way to get around this, there are a couple of ways to improve the spatial resolution in infrared experiments. You can do near field scattering sort of measurements if you like. They're a little bit difficult to use. One way to get around this that's sort of a bit easier to implement in many laboratories is to use photothermal imaging. Okay, and so that's what we have sort of described here. So in our experiments, so firstly, the laser that we use is a OPO. It's has a pulse width of about 10 nanoseconds. And then in the version that we have, it has 2 wavelength regions, one in the 3 micron region and one in the longer wavelength region. And for reasons best known to the people who made the OPO, those 2 lasers have slightly different, well, quite different repetition rates. Most of the experiments that we do are going to be at the 3 micron region at 150 kilohertz, and that's a little bit easier for us, right? Mainly because of the high repetition rate gives you a little bit better signal averaging. Okay, so in our experiments, we take the output of this OPO and we focus it at the sample with the Cassegrain objective, and we make that 8 micron spot size, or even worse, and that infrared beam heats the sample and creates a photothermal signal, and then we detect that photothermal signal with a visible probe beam. And for the experiments at the start, actually most of the experiments I'll talk about, that probe beam was a green laser, and that's quite a good wavelength to use, right? It gives you a nice spot size. So what we do that's different than the other talks that you've seen on infrared photothermal imaging is that we use counter-propagating beams, and so we have the infrared light focused by this Cassegrain objective that we don't like too much, but we focus the probe with a regular refractive objective that gives us a very nice point spread function at the sample, right? So refractive objectives give you much better performance than Cassegrains. So when we get the spatial resolution in this version of the experiment is mainly determined by the probe beam. And so we get much better spatial resolution using both the visible probe and also these nice refractive objectives. And indeed, we can do experiments with oil immersion objectives and get very small spot sizes. Okay, so this is how we do it. We do it with a counter-propagating scheme. And as was discussed a couple of talks ago, right, for sort of applications, right, many applications, this is not that convenient, right? Lots of experiments or lots of applications, it's just a lot better to have the light going through the one objective. If you do that, you have to use a Cassegrain, and so you lose a little bit of the performance that you gain, that you get from using a refractive objective. So mainly, right, we have counter-propagating beams and we detect the reflected probe beam off a surface that's near where the sample is. And as we scan the sample through the focused laser beams, we see a PHI signal that tells us about the sample. So over on the top right here, these are some images of about a 0.5 micron polystyrene beads, 2 beads that are close together. And the bottom image here is a line scan, or the bottom graph is a line scan through an image that was collected with a very much smaller polystyrene bead to really test the spatial resolution. And so the full width half maximum is about 0.3 microns. So compared to what we had in the previous slide with just infrared imaging, we get about a 30 times improvement in the spatial resolution. Okay, so spatial resolution that's really sort of just determined by the visible laser beam. Okay, so this is the important thing about this experiment, right, is that we're measuring the infrared absorption of the sample. So the information about the sample comes from the infrared beam, but we're detecting, or we're getting that, the spatial resolution is determined by the visible probe. So these are sort of some control experiments here. At the top, there's some images again of like half micron size polystyrene beads. The A, B, and C are experiments done in the 3 micron region. And we have in the middle here a spectrum of the bead taken by scanning the wavelength of the OPO, and then comparing that spectrum to an infrared spectrum of polystyrene beads that we took in a different experiment. And so the spectra are very close to each other. The bottom row of images is the same thing in the other wavelength region that we have access to in about the 1.5 micron region. So the spectra again match the infrared IR-PHI spectrum, match what you have in the FTIR spectrum. And the spatial resolution again is equivalent. Actually, it looks slightly better than what we had in the 3 micron region. So the spatial resolution is just determined by the probe. We don't need to worry about the wavelength of the infrared light in getting spatial resolution. So we also did an experiment in this paper where Jeremy was the lead author on just a patterned polymer film, just to sort of check that you can see images that aren't just little beads that scatter light. So you can sort of reproduce. So this is a polymer film where we had used photolithography to make marks, and so you can reproduce the image, the patterns in the film fine. And you also sort of see in these images, there are these waves going through the images. These are sort of differences in the height of the polymer film that's created when we spin coated the polymer onto the surface. So we can get information about this, sort of the texture of the films. Now, when we did these experiments, the typical way of doing PHI, the most common way, is to put your absorbing object onto a glass slide and then surround it by some sort of liquid that creates the thermal lens. So in the IR, right, that's difficult, right, because most of the common liquids that you use for these experiments have strong infrared absorbances in exactly the region where you're trying to look for your sample. So you can't use liquids like glycerol or water very easily to sort of amplify the signal and create a thermal lens. We did some experiments to try and use carbon disulfide, but it didn't smell very good and it didn't work very well. So we don't do that anymore. So these experiments here, they're just dry samples, right? They're polystyrene beads on a glass surface. And so one of the questions that we had when we started this work was, where does the signal come from? And so to look at that, we did some COMSOL simulations, and I'll spend a little bit of time talking about this, and we'll talk about some other COMSOL simulations if we have time at the end of the talk. And so Ilya showed these, and so I'll sort of go over them in a little bit more detail. So we wanted to be fairly careful in doing this, and so we wanted to model both the absorption of the infrared light and the scattering of the visible probe. And I should say that right at the start, these simulations, Frank gave a wonderful talk on simulating PHI signals and with different levels of complexity. These simulations, in some sense, are at the simplest level that Frank talked about. What we do in the simulation is that we calculate the change in scattering of the bead for the visible probe beam, and we equate that to the PHI signal. So this is a sort of an optical theorem approach to what the signal is. We're not doing anything very sophisticated in modeling how the bead scatters the light and how the signal is detected. We're just going to calculate the cross-section, scattering cross-section, see how that changes when we heat the bead. So the model has a polystyrene bead on the glass surface, and this is a sort of a snapshot from COMSOL of what that model looks like. The bead here is in the middle. The first step is to calculate the absorption by the infrared light that heats the bead. Now, when you do that calculation, the infrared wavelength is very long in this in these experiments compared to the size of the bead. So you're simply really in the quasi-static region. Okay, when the IR light goes through the sample, it evenly excites the polymer in the bead, and the absorption cross-section that you calculate from COMSOL is consistent with what you calculate from mean theory, and just the sort of the quasi-static version of mean theory. So there's nothing particularly complicated about it. The simulation that we had 3 steps: the excitation step, then we use that information, basically the absorption cross-section, to model heating. And the way that we model the heating is that we say that we have a 10 nanosecond heating pulse that goes through the bead, and we just use the power of the heating just matches what we would expect based on the absorption cross-section of the bead and the power of the laser beam. And so we say that the bead itself is just a heat source in the model, and then we calculate how the temperature changes in the system based from that heat source, and the power of the heat source comes from the absorption cross-section and what we know about our laser beam. Okay, so that in COMSOL we calculate the temperature change in the system from this heating from the bead, and then from that we calculate the change in the refractive index of the bead, or everything actually in the system, and the expansion of everything in the system. And we use that to calculate how the scattering changes. And so maybe it's a little bit clearer now to show that. So this, hopefully this will work again if I click on it. So this is the temperature change as we have a heating pulse going through the sample. Now, it's important to remember that the bead is evenly heated here, right? It's in the quasi-static region. The light evenly excites the bead. And what you see is a large temperature change in the bead and in the air. And it looks like the temperature is not evenly distributed through the bead. Now, the reason for that is that the bead, the polystyrene bead, is sitting on a glass surface, and heat is going from the bead into the glass. Okay, and so that is, as you take away the heat, right, you sort of get this uneven distribution of temperature within the bead because the energy is flowing out into the glass. You can see that there's, if you look very closely, there's a change in the temperature of the glass. There's a big change in the temperature of the air, and you know, as the pulse goes through, heat up the bead, but the heat goes out very quickly into the environment. Okay. If you look at the refractive index changes, and we can look at the change in the refractive index, we allow the refractive index of both the air that the bead is in, right, and the glass surface to change, as well as the refractive index of the bead. This is what it looks like. Okay, there's a big change in the refractive index of the bead. There is essentially no change in the refractive index of the air because air has a very, very small refractive index, so it just doesn't count. And there's a small change in the refractive index of the glass. And that seems to mainly be because glass has a pretty big heat capacity, and so there's not really a big temperature change in the glass, right? We heated the bead, big temperature change in the bead, heat flows into the glass, but there's not a huge effect on the glass. So if you look at the refractive index change, most of it is in the bead. Likewise, in the expansion, it's essentially the same story. Big changes in the displacement or the size of the bead, not much change in the glass, and of course, nothing really in the air. So the heating is localized to the bead. That causes changes in the refractive index and the expansion and the size of the bead, and that changes the scattering of the bead, and that's the signal essentially that we see. Okay, these things will all run again as I click through them, and we go to the next slide. This sort of captures that idea, right? In terms of temperature, you get a large temperature change in the air, but it doesn't matter because there's no change in the refractive index of the air. Most of the changes in refractive index and displacement occur within the bead, and that changes the scattering cross section. And then in this idea of modeling it like through the optical theorem, that gives us our PHI signal. And we've not done anything very complicated with the modeling. In the simulations, we just use COMSOL to calculate the scattering cross section of the system. We include the bead and the glass surface and the area, but it's all from the bead. And so these are the results at the bottom row here of how the cross section changes with time for 2 different diameter beads that are sort of representative of what we looked at. Now, Okay, the heating decreases the refractive index of the bead, which causes a decrease in the scattering cross-section, and it increases the size of the bead, which causes an increase in the scattering cross-section. So in these calculations, we separated out those two effects, or we did calculations that included both the change in refractive index and the displacement. And then we also did calculations where we just had the refractive index change, or we just had the displacement change. Okay, and so we can look at those two effects separately. So they sort of counteract each other. They play off in each other. If we look at the small bead, so the green line is the change in the cross-section, scattering cross-section, just from the change in refractive index. There's a decrease. The red is the effect from thermal expansion, and the black line here is those two effects included. So you can see for a small bead, 100 nanometer diameter, the change in refractive index beats the change in the from the thermal expansion, and so there's an overall decrease in the scattering cross section that gives you the signal. When you increase the size of the bead, now we see in the simulations that now the effect from the thermal expansion turns out to be bigger than the effect from the change in refractive index. And so now thermal expansion wins. That's what determines the signal. And importantly, there's now an overall increase in the scattering cross-section. So in principle, the sign of the signal ought to be different if you compare a small bead to a large bead. And we did try to look for that, but we weren't very successful in trying to sort of see a change in the phase or the sign of the signal in our experiments. Right, in these calculations, right, for the infrared excitation, as you said before, you're in the quasi-static limit. But for the visible light, these beads are very large, so you either have to do a simulation or a full mean theory calculation to calculate the change in the scattering cross-section. And so that's quite complicated. And so these effects from thermal expansion and refractive index have a rather complicated effect on the signal. Overall, the PHI signal, right, gets larger as the diameter of the bead increases for a constant amount of heating, but there's this change in sign issue, right? So we would predict a change in sign somewhere between 0.6 and 0.7, 0.8 microns, I should say, for polystyrene beads on glass. So there are certain sizes that would be rather difficult to see for this particular experiment. But that's the emphasis of the signal, you know, where the signal comes from the beads, the change in their scattering cross-section. Okay, so I want to talk about the one, I think, main application that my group has looked at for this. Ken is doing work on using IR-PHI to look at semiconductor systems, and Ilya talked a little bit about that. We're very interested in plasmons and metals, and so the experiment we were interested in was to see if we could use these infrared PHI to look at plasmon modes of gold nanowires. And this idea of looking at these systems was inspired by a talk my colleague John Camden gave at Notre Dame, where he used STEM-ILS measurements to look at plasmon modes in gold nanowires, right? So we're going to look at the same nanowires. In STEM-ILS, right, you're looking at, you have an electron beam going through a sample, and you look at the loss of the energy out of the electron beam. So you can see resonances, nanostructures. And the spatial resolution there is, of course, great, right, because it's determined by the electrons. And so you can map the plasmon modes in different structures. And so over on the left here is an example for a triangle. If you look at nanowires, you can see the same things. You can map the plasmon modes in the nanowires. So in STEM-ILS, and I should say this is not just John's work, this is also done by in collaboration with David Masiello. So these are some STEM-ILS measurements of nanowires, and what you see are a series of resonances that are called in the field Fabry-Perot modes of the wires. They're plasmon resonances, and they are just standing waves of the plasmon moving up and down the nanowire. So you in electron microscopy or electron spectroscopy, I guess, experiments, right, you see all the different modes, and you label them by a mode number, right? So you have a dipole is number 1, and then you have, successively higher modes, 2, 3, 4, and you see all of those in the electron microscopy experiments. And if you take some random length nanowire, I don't know, we'll just say, boy, what would be a good one to look at? The ones we looked at are about 3 microns, so we'll look at this one here, right? You'll see these modes, but if you don't have any further information, right, you don't know which one of these resonances corresponds to which mode. So if you do an imaging experiment in eels, then you can look at essentially the form of the plasmon, and you can assign the mode. Okay, and so that's what they've done in this experiment. So by looking at the images, they know, for example, that this one here in the purple is number 2, that one's number 3, and so you can assign these modes and then learn about the modes. Okay, so this is kind of an interesting thing. These resonances are in the IR. For people who work on plasmonic materials, that's sort of an interesting mode to look at. And of course, they're kind of in the region that we can get to with our instruments. So we thought that we'd like to try and see if we can see these modes and learn something about them. Okay, so this is the result of the experiment. It's best to maybe talk about the spectra first. They're all done in about the 3 micron region, which is the region for our laser that works best. And so these are spectra for different length nanowires where you very clearly see these resonances. So if we just look at panel A, if we start at 2.5 microns, make the nanowires longer, you see a resonance that shifts to longer wavelength. When you get out to this 3 micron wire here, there's a second resonance that's appeared here. So this is one of these modes, and then over here, this one's another one of these modes. As you make the nanowires longer at 3.5 microns, you again see 2 resonances. As you make them increase the length from 3 out to almost 4 microns, this lower frequency mode kind of disappears out of the region that we could monitor, and this mode sort of goes to lower and lower frequency as the length increases. These are these Fabry-Perot modes. This formula up here is a sort of an approximate formula for the frequency. So the frequency depends on the mode number and the length and the effective index that the wire is. Now, in eels measurements, you excite all the modes. In optics, if you had a perpendicular excitation, you would only expect to excite the odd order modes, the 1, 3, 5. Okay. Now, the Cassegrain, we're coming in at an angle, so actually that selection rule doesn't apply. In principle, we can excite all the different modes. But we have the problem that you have in eels, right, is that we don't know which mode is which. And so to do that, we recorded images. And the imaging part leverages the super resolution capabilities of infrared photothermal imaging, right? So the spatial resolution in the experiments is much greater than, much better than the IR. It's determined by the visible probe. And that allows us to sort of map out the absorption of the infrared light in the nanostructure. So when we look at these modes here with the asterisks in panel A, we see very consistent 3-lobe structure. So that 3-lobe structure allows us to assign that mode to the, or that resonance to the M=3 Fabry-Perot modes. And then based on that, we can assign this other mode that we see here to the M=4. Unfortunately for the M=4 mode, we do not get as nice images. They're not very consistent, and they look, they look sort of a bit of a mess. So it's not very easy to get too much information out of that, but we're quite happy with the information we get for the M=3 modes, and we can do that in assignment. So from the images, we can assign the modes, of course, if you just did a straight IR absorption measurement, you could not resolve this structure, right? It's not possible. The ability to resolve the structure comes about from the super resolution capabilities of the technique. So this panel here is a plot of the frequencies of the modes plotted versus m divided by L from this formula up here. You can sort of see it basically fits the Fabry-Perot formula that was derived by Bill Sage a fair while ago. You can sort of see that there's a difference, a slight offset between the two M=3 and M=4 modes. It's not predicted by this simple formula. So things are actually a little bit more complicated than this formula. The lines here are finite element calculations done by David Masiello's group, and you can see that the finite element calculations do a very good job of matching the experiments and predict this offset, or show that this offset is a real effect in the experiments. Okay, so that's a sort of a demonstration. Now, so to some extent, right, you don't learn anything new compared to what you learn in STEM eels. However, this experiment and the range of wavelengths that we can look at is much more limited. But of course, this is a much cheaper experiment than a STEM eels experiment, right? It's a desktop system. These are the finite element calculations done by David's group. These are the spectra, right? So you see in the calculations show that you should see when you come in at an angle, right? You should see all the different modes. The intensity should be much stronger for the m=1 mode, but that's outside our detection range. We weren't able to detect that mode. We're just sort of seeing the m=3 and m=4 modes. This is a map of the heating in COMSOL language. That's resistive losses. That's the heating for the m=3 mode of the gold nanowire. And it shows you that 3-lobe structure that is what we saw or claim to see in our images. One thing that's a little bit, well, odd about these experiments is that, of course, right, you heat, the heating creates a temperature distribution in the nanowire that will match, or initially will match this simulation. But then, of course, you know, gold is a pretty good conductor, so there's very rapid heat diffusion in gold that should smear out this structure. So these are some images done by simulations done by David that sort of take into account heat diffusion. So we have this initial absorption, and then we're again modeling a 10 nanosecond Gaussian pulse and looking at how the temperature changes within the nanowire, allowing for thermal diffusion of the electrons in the wire. And the simulations show that very quickly, right, that absorption, that structure in the absorption is lost due to thermal diffusion, right? So this is sort of why the images that we see are not as well pronounced as what you get just from the resistive losses. They suffer from this thermal diffusion that sort of wipes out the structure in the images. For some of the images, the structure looks a little bit distorted, and that's probably because the Cassegrain is not particularly well aligned, and so we have more excitation from one side than the other, which sort of distorts the images, and that's sort of some calculations of that effect. So in these experiments, right, it's nice that we saw any structure, because the prediction is that structure gets washed out very quickly. And it sort of brings up that there's issues in photothermal experiments about thermal diffusion. And so we want to understand this a little bit, and that's sort of some recent work that we've been doing, is to look at this, this issue about thermal diffusion. And I'm sorry, I forgot one more slide about this. I would say, you know, I've been pretty complimentary about eels. It's a beautiful experiment. You can get a lot of information. The one advantage you have in optics is, of course, that the spectral resolution is better than what you can get in Neal's microscope. So we can very accurately measure the line widths of these resonances. And this is something that's sort of interesting, right? So for these modes, right, in the infrared region, the dielectric properties of the nanostructures are determined mainly by the Drude contributions, right? This is this very well-known model of the dielectric constants of metals. And so the line width that you should expect when you look at the resonances should be the damping parameter that's in the Drude model. And that's been measured for gold quite extensively. Okay, so you would expect to have a line width that's determined by this parameter. And depending on the dielectric constants you look up, you have different numbers for this parameter. And so this orange area here indicates the range of the different parameters that are in the literature. At the top here, it's the values of Johnson and Christie dielectric constants that just about everyone uses, around about 75 milli EVs for this parameter and therefore the line width. At the bottom here, a much lower value is the ones, the dielectric constants recently measured by Raschke's group, which are probably a little bit better, but no one seems to use those. Our experiments are, of course, for whatever the dielectric constants are for those nanowires that were fabricated. The lines here are, again, the simulations, and these simulations use Johnson and Christie's dielectric constants. So what you see in the simulations are that the line widths are narrower than what you'd expect from the dielectric constants of the metal, which surprises me. I think that's a very interesting result. David thinks it just sort of naturally comes out of the simulations, and it has to do with the fact that the field in these metal nanostructures in the infrared is, most of it is on the outside of the metal. It's not really feeling the metal as much. And so you end up with narrower line widths than what you'd expect just from the Drude model. So as the frequencies go down, you get more and more out in the infrared region, the line widths go down. You see that both in the experiments and the simulations. And we can get line widths down to about 35 milli EV out in the IR, which is much narrower than either the Johnson and Christie or the Raschke values for the Drude parameter, which again is something that's interesting to me, but it comes out of the simulations. And also, you also see that in STEM EELs, and that's this panel on the right-hand side. Okay, so let me talk a little bit about work that we're doing right now, looking at this issue about spatial resolution and thermal diffusion. And the interest that we have in this is really to try and understand the resolution in the IR-PHI. So compared to conventional conventional photothermal measurements, right, where you have visible pump and probe, right, the situation is a little bit different in PHI. In the infrared version, you have this very large pump size, and you also have sometimes much lower repetition rate laser systems, and both of those could affect the spatial resolution. So to try and understand this, we wanted to look at how the spatial resolution depends on the repetition rate of the excitation. And the motivation for this is that this is this formula for the change in temperature in the environment that comes from Carslaw's and Jaeger's book. That tells you about how temperature should change, and it involves the thermal diffusion length. The thermal diffusion length depends on the frequency of the experiment, and as you go to low frequencies, you expect very large thermal diffusion length. So we wanted to see if this is an effect. Okay. One thing to note about this formula, and this Frank also talked about this, is that at very long times, right, essentially the temperature distribution just goes as this 1 over R term here. Okay, and so this is what we might expect at very long frequencies. Okay, so this is an experiment where we actually use a visible pump and probe, and we focused it on the sample. We're using visible light here because we can very easily change the repetition rate in the experiment. And these are just for gold particles in glycerol. So these are experiments done at different frequencies for a collection of little gold particles, and going from about 100 kilohertz down to very low frequencies. And what's sort of noticeable in this experiment, both the pump and the probe are focused, but there's really no change in the spatial resolution, right? You can go to very low frequencies, and there's no real effect in this experiment from thermal diffusion. The image here is just determined by the pump laser. Okay, so that's our understanding of the experiment. And to sort of demonstrate that a little bit more clearly, let me show you some other experiments. So firstly, that last experiment was when we had the pump and the probe focused together so they're both diffraction limited. We can also adjust experiments, adjust the focusing conditions. So we blow the pump beam up at the sample. And when we do that, and then we look at how the image changes with repetition rate, now we do see an effect that is essentially due to thermal diffusion in the medium, right? So now this top panel here has a very large pump beam, again, a diffraction limited probe, and we're imaging the same gold particle at different frequencies. Okay, so at 500 kilohertz, you can compared to 10 kilohertz, right, you can see that there is a increase in the size of the image, right, that we would believe is due to thermal diffusion effects in the environment. This bottom set of images here is a comparison of 4 gold particles, where firstly we have the pump and the probe focused, right? So diffraction limited pump and probe. We see an image that is essentially determined by the spot size of the pump. And if we blow the pump up at the sample, now we see that things are much larger. The images here sort of smear together, and we're getting effects in the images presumably due to thermal diffusion.
So, Greg, we should leave a bit of time for the discussion. So you should move to the conclusion.
Okay. All right. So so this is some modeling of this. So very quickly, what is happening here, right, is that in this system, you very quickly reach thermal equilibrium, right? You reach a steady state temperature. This is the temperature in the particle, steady state temperature in the particle. And so a steady state distribution of the temperature in the environment. This is a fit to 1 over R that shows it's sort of a, you get that distribution. So the size of the image is there's some effect from thermal diffusion, but it's not very large because it's just the temperature is falling off as 1 over R. It's nowhere near what one might naively think for the from the thermal diffusion length. Okay. And so these are sort of some simulations at different frequencies over 2 periods, over different sizes. And so you see a smearing of the images from when you go down to low frequencies, but it's not a huge effect because it's just going as 1 over R. And if you do a regular PHI experiment where you have the pump and probe both focused to very high spatial resolution, you don't see thermal diffusion because you only create the thermal lens in the sample when the pump beam is on top of the particle, right? So you're always going to be determined, the spatial resolution will just be determined by the spot size of the pump, right? So that's the main thing that we get out of that last part of the experiment, right? So thermal diffusion doesn't affect the spatial resolution when the pump and the probe are diffraction limited in a regular experiment, because you don't get any heating unless you're sitting on top of the particle. So in normal PHI experiments, the thermal lens doesn't affect the spatial resolution. What you're doing is you're just imaging absorption of the pump beam. In IR-PHI, we have a larger pump, and you sometimes have slow repetition rates. Now you do have to worry a little bit about thermal resolution. That is going to degrade the spatial resolution. But it's not going to be a huge effect because the temperature just falls off as 1 over R. So it falls off fairly quickly from the heating source, right? You reach thermal equilibrium quite quickly. That's what the simulation showed. And then the last 2 conclusions here are just about the Fabry-Perot measurements. It's interesting that we actually managed to see any structure in the images. And from my point of view, it's seeing very narrow line widths was quite surprising in these experiments. Work here has been funded by the National Science Foundation, and thank you. And so let me sort of escape out of this, and I'll be happy to answer any questions.
Thank you very much, Professor Hartland. In the name of the whole audience, we are not. It's not possible to applaud, but I am applauding locally for all of you, all of us. So I suppose there are questions. You can either use the chat to ask your question, and I will give you the word, or you can. I see already a question by Frank Sichos, or raise your hand with the raise hand option of your Zoom panel. So Frank, go ahead, please.
Yeah, only a short question. Thank you very much for the nice talk, Greg. So at the beginning, I understood right, if you do the simulation of the signal, then do you have the sphere just in a point contact with the substrate? And since the cooling is due to the substrate, does the choice of the substrate make a big difference for the signal?
Yeah, thanks, Frank. Sorry. No, it's not a point contact. So I think, I think your question gets to that choosing that area has an effect on how quickly the heat's going to flow out of the particle. And so we essentially made something up. The details are in the supporting information, that paper, but I don't think it shows up very clearly. But we chose some sort of area here to have a contact. We didn't think a point contact would be very realistic. So you have to sort of model some sort of contact here. And you would expect an effect from the substrate. You know, most glass, silica, most sort of dielectric materials are kind of similar in terms of their heat conduction properties. So I think you'd have to go to a rather sort of very different sort of material to see a big effect. So there should be an effect. We didn't look at that.
Okay. So I know maybe other people ask questions. I can either do that in the chat or in the email.
Well, I see no urgent question. I have a few myself, but I think Frank, you can go ahead.
So I just wanted to ask if the nanowires were also just on a substrate and in air without any kind of medium when you study them.
Yes, they are. The nanowires that we got were from a collaborator down in Tennessee. So these are actually nanofabricated, and so that's an image out of one of the wires. So they are in very intimate contact with the substrate.
Okay.
Right. So heat is going to flow very quickly out of those wires into the substrate. Now, presumably in David's calculations, so these calculations are a little bit beyond what we can do, or at least what I can do. So in David's calculations, that should be included, right, in the calculation. So, but it's a bit of the same story as what happened with the beads, right? So even if the heat flows into the substrate, the main effect in the dielectric constants is going to be in the metal. So you're kind of imaging the metal.
Yes.
And also once the heat's gone into the substrate, right, you wouldn't expect to have any sort of structure. So we must be in the images, as smeared as what they are, we must be seeing the metal, the dielectric constant change in the metal, to get the structure out of the image.
Okay, thanks.
Okay, we have another question by Subhasis.
Yeah, so I have two quick questions. So one is regarding the PHI signal, depending on the particle size, where you have two effects playing role. One is thermal expansion, and another is the scattering by the diffractive index. So it's very complicated. So can you predict that which particle size limit you can detect using your sensitivity? Because if you go very small particles, so what is really major playing role? Can you decide from your theory? So this is one question, and second question will be related to the spatial resolutions or the point phase function, depending on the frequency. If you eliminate with a diffraction limited pump beam or the wide field, I didn't really get. Maybe you have explained, but didn't get why they are different in the spatial resolution, because at the end the spatial resolution is defined by the convolutions of the thermal lens and the probe beam, right?
Yeah, I think I did. For the second question, I think it's clear I didn't really explain that very well, and so I'll go back and try to sort of say that again, and I apologize if I just say the same thing twice. So your first question is, well, yeah, you can certainly simulate the beads. I would say for small beads, it's going to be the refractive index that has the main effect, right? And so you can sort of estimate the size. Ilya did a more detailed study of this, and I can send you that paper if you like. Sort of more detailed than what we have here, study of these effects for a couple of different materials.
Greg, if I may ask you there, because it's not obvious for me why there is this very non-intuitive cancellation of the two. I would naively expect, that the temperature causes both a delta N and a delta R, but that, of course, this would be, the ratio should be constant. It's not like that, obviously. So is that an elasticity problem? Because you have to solve the continuous medium equations of the expansion of the bead. What is the physical reason for that? I don't see very well.
No, I think it's more a me theory issue, right? Is that the scattering cross section doesn't scale linearly with dimensions or refractive index, and maybe it scales linearly with the refractive index of the particle, but it doesn't with dimensions, and they enter into it in the calculations in a slightly different ways. So they're
but in me theory you scale everything by the radius. The radius disappears, so it should not change with radius, and it does.
Well, this is the in the dipole limit. I mean, firstly, in the scattering of the visible light, we're not in the quasi-static limit, right? You have to use the full me theory to get that out.
Okay, so this is due because of me theory and the scaling. You're not in the static approximation anymore.
We're not in the static approximation for the visible.
Okay.
Right. At 1 micron, right, the beads are actually bigger than the visible wavelength.
Okay.
Right, so we're way out of the static approximation in the visible. We're in the static approximation for the IR, but not the visible, and that's the reason.
I get it. Thank you very much. Yeah.
Okay. So if we hopefully that's okay. And so in COMSOL, right, the COMSOL includes everything, so it's also not, it takes into account that effect. Let me go back to this experiment, which I kind of rushed through. So I think the key thing, right, is to look at this image down here, right? So one of this was done with what's diffraction limited, right, but a focus pump and a focus probe. And we scan over 4 particles at 10 kilohertz, right, quite a low frequency. And this image is where we do Michel's trick, and we put a lens in front of the objective for the pump. We blow the pump up at the beam, at the sample. So we have what we call a wide field pump, but it's not, it's not covering the whole sample. It's sort of much bigger than the probe, right? So it's a big pump beam, and so now the spatial resolution is determined by the probe. So I would say in the wide field image, it's what Sapasis was saying. The resolution is a convolution of the probe and the heat diffusion into the sample. Okay. In the focus image, you still have heat diffusion in the sample, right? But you only have any heating when you're sitting on the particle with your pump. If you move off the particle, you don't heat. So there's the thermal lens is irrelevant, right? Yeah. You create the thermal lens only when you sit on top of the particle. So here we have a thermal lens that's much bigger than the particle, but we're not, when we're off here, right, in this region, we're not imaging it because we're not heating the particle.
Yeah, thank you very much. Yeah, I think this is quite clear now to me.
Yeah.
Thank you.
What you could do if you wanted to, and if people thought this was a great idea, we'll tell Brendan to go do it. You can sit on the particle with your pump, right? And you can scan the probe over the particle. That trick is done quite a lot in transient absorption microscopy. Then you could image the thermal lens, right, with a point excitation. Okay, that's a bit of a difficult experiment for us, but we could do that. So you would be able to image the thermal lens and do it at different frequencies, but that's not it's kind of not the point we're trying to make here. It's that when you do a regular experiment with focus pump and probe beams, you're imaging the absorption. You have a thermal lens that gives you the signal, but you're not imaging it because you're not creating that thermal lens unless you're on the particle.
Yeah, thank you.
Sorry.
Okay, maybe I can allow myself a last question or discussion about the medium that you mentioned, that usual molecular liquids, even water, have obviously an absorption in infrared, and that's annoying. How about using, for example, supercritical xenon that is extremely sensitive, right, and has no absorption whatsoever in the infrared?
Yeah.
So have you considered that, and how difficult would that be?
I did, because I read your paper on this. It's beautiful, very beautiful work, and I thought, well, boy, that would be a great idea. But of course, setting that experiment up would be difficult for us. No, I think that would be. There might be other materials that you could use. That would be one of them. As I said, we tried carbon disulfide, and we couldn't really get that to work very well, and so. Then we thought, well, we can't get carbon disulfide to work where, supercritical xenon's going to be harder. So It would be.
Well, no, we had a very good American student who did this project, and she needed only 3 months to set up this experiment, so it's doable.
Okay.
Good workshop, a good student.
Yeah. Yeah. I think that's. I mean, it's a great idea, but the real thing, the real applications are what Zhixing Chen talked about in biological systems, right? So I think it's more of how do you deal with the water that you have.
And also another technical question is about the in the case of the objectives, you say you like better refractive objectives. So
yeah,
are glass objectives really a problem in the in infrared, or because there are some not refractive but reflecting objectives based on glass, which are Cassegrains as well, which may be of better quality than yours. So have you thought about that? Or is it excluded because of the infrared absorption of the silica glass?
No, I think we have thought about using different objectives, right? And Ken has thought a little bit more about this than I have. We're not very good at using Cassegrains, at least certainly when we first started these experiments. So it's quite possible there are much better objectives. So that would be worth exploring. So yeah, I think the development of objectives that can transmit both IR and visible would be quite valuable, and I think there are some developments in that. We do just use these cheap Cassegrains, a couple $1,000 Cassegrains that you buy, and use a refractive objective on the other end. But that's certainly, having a better objective would improve this experiment. And if it is much easier to do things, or more convenient to do things co-propagating rather than counter-propagating. This is a bit clunky to do it this way.